This is the study session on portfolio management and the reading on portfolio risk and return. This is part 1. This ought to be called Portfolio Risk and Return. This is the most fun that we're going to have in the entire CFA Level 1 program. We're going to do lots of calculations in this particular reading, also in part 2, but it's going to be really, really fun stuff. We're going to base all of our decisions on the work of the founding fathers of finance, this modern portfolio theory that was developed by guys like Harry Markowitz and William Sharpe and a bunch of others. So let's get right to the LOS. Here's a good one. Calculate and interpret major return measures. And so this is what we're trying to do. We have a financial security and it performed over some time period, and we need a measure of that performance. So we call it a return. So let's look at this first one. I bet you guys have heard of this one before. Holding period return. This is really a measure of the change in the value of an investment over a particular time period. Now, the problem with the holding period return is the identifiable holding period. It's one thing to say, hey, I generated a holding period return over the last year of 10%, or I generated a holding period return of 10% over the last 50 years. So make sure you're sensitive to the holding period return. But the interesting thing about a holding period return is that it can include, and it should include, any intermediate cash flows paid to the owner of the security. So there's a good formula there. Start with the ending value, take out the beginning value, and then add any income generated by the asset. For example, dividend income and interest income on a bond. And then divide by the beginning value. And there's a good formula there. So we can do a quick calculation here. 5 years ago, a trader paid $20 per share for 500 shares. Current price has grown by 50% of the purchase price. The shareholder has received 12 dividend payments, each amounting to 50 cents per share. And if the trader decides to sell those shares today, what will be the holding period return? And so we need to start out with some calculations. We need to figure out, what did we start with? So we take the 20 times the 500, that gets us a $10,000 investment, and then increasing by 50% gets us up to $15,000. So that's a 50% holding period return without the consideration of the dividends. But then if we add those dividends in of $3,000, then we're going to get an 80% holding period return. So that's 80% over 5 years. Make sure you're sensitive to the time period and all of those intermediate cash payments. Arithmetic return, that's really just the simple average. And so if we have a financial security that returns 25 and 10 and 12 and a minus 3% over the last 4 years, all we're going to do is sum those and then divide by 4 to get 11%. Now, at the risk of sounding basic and at the risk of offending you guys, make certain on the exam that you make any of those returns that are negative. Make sure you HP guys hit the change sign button, and make sure you Texas Instruments guys hit your plus minus so that you keep track of positivity and negativity. Now, a little bit later on in one of the slides, I'm going to show you a different way to compute that arithmetic mean, and you're not going to like the way that I show you, but then you're going to thank me for showing you that way when we have to do something else. But we'll just hold off on that for a few slides. Another return measure is the geometric mean return. And note that when you compute the arithmetic mean, if you're going to divide by 4 in that earlier example because there are 4 time periods, and it does give you an average. But what I want you to do is consider the following. Suppose that I was your money manager and you gave me $100 today and said, hey Jim, invest this $100. And during the course of the year, I turned it into $200, right? So we went from 100 to 200, that's a 100% return. And then let's suppose that during the following year, I turned your $200 back into $100. So that's a 50% loss. Well, what's the arithmetic average of my performance? Well, you take 100, subtract out the 50, divide by 2, I average 25%. So if we're using arithmetic returns, I can come to you at the end of that 2-year period and say, hey, I averaged 25%. Where's my raise? And you're going to look at me and you're going to say, wait a minute, Jim, I gave you $100 2 years ago, and 2 years later, I'm back to $100. There's no way that's a 25% return. So the arithmetic return can be misleading. That's why we do the geometric return. What we're going to do is we're going to consider the effects of compounding. What we're going to do is we're going to take 1 plus that return, and we're going to multiply all of those, and then we're going to raise it to the 1 over the n power, and then subtract 1. And so this is much more meaningful. It reflects a change in the wealth of the client or the investor. So with that example that we did under the arithmetic return, we'll take the 125 and the 11 and the 112 and the 0.97, multiply those, raise it to the 1/4, subtract 1, and we're going to get 10.6%. Now, if you compute the geometric mean of the example that I gave you before, I had a 100% return, right? So 1 plus 100, that's 2, right? Then I had a 1 minus 50%, that's a half. So what's half of 2 is 1, raise it to the 1/2, minus 1 is 0%. So the geometric return is 0% when you gave me 100 and I ended up with 100 after 2 years. So notice the LOS asked you to calculate and interpret. So we did the calculation, so that should be pretty straightforward. But the interpret one, that's really an important part of the LOS. So make sure you remember that the geometric return does reflect compounding, and it reflects the change in wealth. Now, a little side note here, a geometric return, it is an internal rate of return. It is a yield to maturity. So we have different names for all of these kinds of things, but they are all geometric returns. A money-weighted return, on the other hand, is going to reflect cash inflows and cash outflows from a fund. And there's no doubt that this money-weighted return is a geometric return, and it is an internal rate of return and a yield to maturity. And so just remember to interpret that money-weighted return as unique to each individual client, while the time-weighted return is going to be specific to a fund or a portfolio manager. And then an annualized return, this is important in turning other than annual holding period returns into annualized ones. All right, so that if we have a monthly return, a monthly holding period return, and we want to annualize it, we're going to take 1 plus that monthly return, raise it to the 12th power, and subtract 1. If we have a 5-year return, we're going to do the same thing, but raise it to the 1/5. And so we're chopping it in the compounding by using the fraction rather than just divided by 12. Now, at the risk of offending you guys, and you won't believe this when I tell you this story, but in my classes, when I ask students to compound annually from a weekly return, I have had students who've said to me, oh, I'm going to raise that to the 48th. I've had students raise it to the 50th. I've had students raise it to the 53rd. So let's just remember that there are 52 weeks in a year. All right, how about a portfolio return? Portfolio return is really just a weighted average of the individual returns on the individual assets. And so if we have 2 assets and we have 40% in one and 60% in the other, we're just going to take 40% times the return on one and 60% times the return on 2. How about some other returns? A nominal return, there's the relationship between nominal interest rates and real interest rates and inflation rates. And this is an extremely important concept. This is going to be critical when we put together a policy statement for our client and we come up with a return objective, and then we have to consider the effects of inflation. So this has great applications for later on in level 1, but particularly when we get to level 3. And so all we're going to say is that that nominal rate of interest, the stated rate of interest, for example, on a mortgage loan, that has two components. It has a real return and it has an inflated return, or a rate of inflation component to it. And then the difference between the gross return, which is the return earned prior to deduction, and then a net return is the return post-deduction of fees. And this is really important when we get into presentation standards and we try to figure out, as a good portfolio manager, how can we report our performance to our clients? Do we want to do it in the gross return, or do we want to do it in the net return? We're going to have some good rules for reporting in another reading and at different levels as well. All right, how about describing characteristics of the major asset classes? All right, so major asset classes, what do you think of? You think in terms of cash, and you think in terms of debt, and then you think in terms of equity. And in the old days, those were probably sufficient, but in the new, more sophisticated times, there are subclasses within each of these. So notice what I have in the table here. I have large cap stocks, small cap stocks. Those, of course, are in the equity universe. I've got long-term corporates, I've got long-term government, and then I've got the short-term government. So those, of course, are part of the bonds or the debt component. And then you could even divide those into further subcategories in terms of investment grade or speculative grade bonds, and then global equities and global bonds. And so notice the table tells us a little bit about the average annual nominal returns. All right, so these are nominal returns, and then a standard deviation. And so what do you see there? You see that shorter terms, treasury bills, those things average about 4%, let's say, all the way up to nearly 12% for U.S. small cap stocks. So here's the thing. What you guys are going to need to remember for the exam is probably not exactly those percentages and those nominal returns, but an idea of what you can get out of those different asset classes, and then the corresponding risk. So notice over on the far right column, I have standard deviation of return. And what we learned way back in our undergraduate days, even in our economics days and clearly our stats days, but also in marketing days, we learned that standard deviation is a great measure of risk. Lots and lots of different disciplines use standard deviation as a measure of total risk. Total risk meaning that it's total. There's nothing else out there except for the total. And that's why financial analysts like standard deviation so much, because it measures risk in its totality. Now interpret that standard deviation. Remember, a standard deviation is a measure of the degree of error. And so just look at that large company nominal return of 9.6% and a standard deviation of 20.6%. What that means is that we can expect to get about 10% out of large cap stocks. But we know that every year we're not going to get that 10%. We're going to be wrong. And what that standard deviation tells us is that we're going to be wrong on average about 20% of that 9.6%. So that's a fairly big standard deviation. This is why investors diversify, because investing in one asset class is just it involves too much total risk. Let's add a statistics concept or two here to our discussion. One of the things that those founding fathers of finance in their modern portfolio theory articles they wrote in the 1950s and 1960s and 1970s, they made a really simplifying assumption that the mean and the variance, the first two moments of the distribution, were all that was needed to describe the returns to stocks and bonds. Well, that might be true, but it might not be true. So the third moment of the distribution is this thing called skewness. And what this tells us is whether or not there are more returns on one side of the mean than on the other side of the mean. Remember, a normal distribution is a mirror image on both sides. But if you have positive skewness, you have a large number of small negative values with a few large positive values. Has a long right tail. Negative skewness has a long left tail. And there's some good indications of what you should probably memorize for the exam. Positive skewness means that the mode and the median are less than the mean. Negative skewness means just the opposite. And so think of those long right or long left tails as the possibility of a big return if it's a long right tail, and the possibility of a large loss if it's a long left tail. Oh my gosh, it's a great time for me to mention this concept. The reason that we're so concerned about that long left tail is we have a small probability of having a large loss. That's when we need to bring in this other concept called value at risk. Oh, we're going to do lots of fun things with value at risk later on. And how about this other word here that sounds like some kind of a disease, kurtosis. Now with a normal distribution, when you have those tails typically come and they almost hit the horizontal axis. But kurtosis means that there are fatter tails, meaning that the tails don't ever hit the horizontal axis. Positive kurtosis indicates a peaked distribution, so remember, like a big spike. Negative kurtosis means that there's a flat distribution. All right, how about back to doing some calculations? Let's do the mean, the variance, and the covariance. All right, so let's suppose that we have years 1 through 5 down the left-hand column. We're returning 10.5, 8.5, 6, 12.5, and 13. So those are, think of those as the holding period returns for each of those years. What we want to do, look up at the top, we want to compute the mean and then the variance. Now we can't do covariance because co means you got 2. We'll do that in just a second. We're going to do the mean and the variance. So here's the long way to do this. And there's a good old formula over on the blue on the right-hand side. But this Excel spreadsheet gives you a really good idea of how to do this. First thing we need to do is calculate the mean. So if you sum those 5 numbers and divide by 5, you get 10.1. And then the deviation from the mean is just 10.5 minus 10.1. So there's the 0.4, and you continue to do that down the third column. And then you square it. So the 0.4 becomes 0.16, and so forth down that column. And then you add those, and you get 33, divide by 5, and you get a variance of 6.74. Now, the LOS does say calculate and interpret the variance. And so that shows you how to do it. But I'm not quite sure how to interpret the variance. When my wife and I go to the food store, we don't ever buy 12 squared pounds of potatoes. So it really doesn't have a lot of fundamental or high intuition economic interpretation of the variance. That's why we take the square root to chop it back to its original base. And we call that square root, we call that the standard deviation of the returns. And that's probably way, way more important than the variance, but the LOS does say and require you to compute the variance. Now, remember I said to you that I wanted to show you a shortcut, and you are not going to like the first part of the shortcut. So what I want you guys to do is get out your calculators. There are some steps for the 12C. There are some steps for the Texas Instruments. You 12C candidates, you're going to have to find the sigma plus button, which is located on the bottom right. And you TI candidates are going to have to find your data button and your stat button, which is underneath the 7 and underneath the 8. All right, so I'm just going to go through these quickly, and I want you to pause and make sure that you can compute these things, because this is much faster than going back and doing it this way. Now, with one caveat. All right, so with the 12C, now make sure you do the gold clear sigma, right? There's an F, clear the sigma. So you're just going to do 10.5 sigma plus and 8.5 sigma plus. Enter those all in a row, and each time your register is going to show a 1 and a 2 and a 3 and a 4 and a 5 so that it reminds you of how many numbers, how many inputs you've completed. And then all you have to do is hit the blue 0 and look under the 0, there's an X bar, and that gives you the mean. And when I teach this to students, they say, oh no, I don't want to learn it that way. I want to add the numbers and divide by 5. And that's okay, I get it. But then all you have to do is look to the right of the 0. There's the decimal point. All you have to do is hit your blue decimal point, which is the standard deviation, and that gets you 2.91. Now, this is what you're going to say to me. You're going to say, wait a minute, Jim, 2.91, that's not 2.6. Hold off on that. Let me go ahead and do this quickly for the Texas Instruments people. You're going to hit your second 7 button, which is the data, and then you're just going to enter those 5 things. So you're going to do 10.5 and then hit the enter button, and then down, and then 8.5 and do all that. Once you get those 5 in there, then hit your second stat button, and you'll have to go down a couple times. It'll say LIN for linear relationship, and then it'll give you an N of 5, and that gives you the mean. And then you go down, and it gives you 2.91, and then you go down again, it gives you the 2.59. So this is important. Back here, this what we did is we actually calculated using this Excel spreadsheet, we calculated the population standard deviation. So make sure in the exam you're aware of what is being asked. If you are to calculate the sample, well then just give them the sample. If you're asked to calculate the population, well then just make sure you give the population. Now note under the 12C, I don't have the population standard deviation. It's much more complex. If you want to figure it out, just go to your 12C manual and you'll get a bunch and bunches of steps. And you might say to yourself, you know what, I think I'm just going to do it this way. So I'm going to let you guys pause and try to catch up to the 2.59 and the 10.1. But I'm going to keep going. All right, how about covariance? What we know about variance and standard deviation is how a particular asset returns vary in totality. In other words, what is the total risk of that particular financial security or that particular asset? Well, what do we know? We know that individual assets, they don't live in a vacuum. They live together, just like my wife and I live together, and we have a covariance between us that reflects our interaction. Our life together is much different than if we didn't know each other and we lived in houses just by ourselves, miles and miles apart. So it's important to understand that covariance measures how each stock co-varies with other stocks. So look at the definition I have there, a measure of how two assets relate or move together relative to their individual mean values over time. This is a good definition for covariance. What we're trying to do is say the following. If asset A goes up by 10%, what does asset B do? Does it go up by 10%? Does it go up by 20%? Does it go up by minus 10%? Does it go up by 0%? Well, that's what covariance does. It measures the strength and the direction of a relationship. Now, here's the deal. I bet you guys are saying to yourselves, okay, Jim, this was a relatively cool way to show me how to perform this calculation using a shortcut. Where's the shortcut for covariance? And unfortunately, there's not. So you're going to have to get the shovel out, put your gloves on, and dig and dig. That's the only way you can compute covariance. And we're going to do that here in the next table. But before I do that, let me go ahead and tell you about covariance. Now, covariances can be positive, they can be negative, or they can be 0. But here's the thing about covariances. Not only can they be negative, they could be like a minus 4 million. Not only could they be positive, they could be like a positive 452,000. So you have this gigantic range of possibilities of covariances. And just like a variance is difficult to interpret, remember my 12 squared pounds of potatoes at the food store, Covariance also has its own unique difficulties to interpret. So when economists or statisticians have this kind of a problem, what they do is they divide by the standard deviation. They standardize the covariance, and that's what the correlation coefficient is. So look in the bottom there, correlation coefficient, which is noted by the Greek letter rho. So correlation between asset I and asset J is the ratio of the covariance in the numerator divided by the product of the two standard deviations. So when we divide by the product of the two standard deviations, we are standardizing this term. So correlation coefficient tells us everything that the covariance does, but what we're doing is getting a vice and we're squeezing and squeezing it down to a more palatable range. What's the range of correlation coefficient? The least you can be is a -1. The most you can be is a +1. Now we can wrap our economics arms around it and make some interpretation of the correlation coefficient. So those are two good formulas to memorize there in the middle of the page. That thing up at the top of the page with the R's and the ERs, well, I'm going to show you what those mean in the next table, but I think it's easier not to memorize that formula, but just to look at what's going on here. All right, so let's suppose we have two assets, asset 1, asset 2. And here are 5 years, and there are 5 years worth of returns, okay? So down in the second box, what we're doing is converting those to decimals and then computing the mean right at the bottom. So the mean of asset 1 is 5.2. The mean of asset 2 is 6.1%. All right, so now what we're going to do in that next column is we're going to do the same thing we did back with the variance. We're going to take asset 1, which is 0.05, and we're going to subtract the mean, which is 0.52, which gets us that minus 0.002. And then in the next column, we're going to do the same thing with asset 2. So we're going to take 0.06 minus 0.061, which gets us a minus 0.001. And we're going to do that all the way down. And then we're going to multiply them. So that's really what this formula looks like over here. This thing at the top with the expectations operator solving for covariance, that is the application of the formula here. We're going to multiply those two columns together. Then we're going to sum them. We get the bunch of zeros and a 43. Divide by 5, and we get a covariance with a bunch of zeros and an 8.6. And that's how you compute the covariance. There's no easy way, at least I don't know of an easier way to do this in the calculator. Oh, this is really important here. Calculate and interpret portfolio standard deviation. Of course, what do we know? I've said this to you in other videos. If you happen to hit the Pennsylvania Powerball lottery for $400 million, you're not going to invest all of your capital into Procter & Gamble stock. What are you going to do? You're going to spread it out. You're going to diversify. And so a great introductory question to portfolio standard deviation is to look at a portfolio with just two assets. And so there's a good formula to memorize, one with the covariance and one with the correlation coefficient. Just notice that the portfolio standard deviation, and those are variances, by the way, the portfolio variance is weight 1 squared times standard deviation 1 squared plus weight 2 squared times standard deviation 2 squared plus 2 times weight 1, weight 2, and then the covariance. And then what we can do is we can substitute. Let me just go back here. We can substitute right in that middle formula. We're going to substitute the covariance in right there. So here's the advice that I'll give you. Make sure, what does the LOS look like? It says calculate portfolio standard deviation. So in order to ask this question, you have to be given the covariance or you have to be given the correlation coefficient. So remember which one is which. Remember which one you're given so that you can use the correct formula. And then, of course, just take the square root to get the standard deviation. All right, let's go ahead and work through a calculation. Here we've got asset 1 and asset 2, 80% in 1, 20% in 2. There's our expected return, almost 10%, almost 16%, and a standard deviation of 17 and a standard deviation of 30. and there's a covariance of 0.005. Now, before we do the math, I want you to think about this. Let's suppose that we're starting with asset 1. We have a 17% standard deviation. That's an average degree of error. What we're going to do is we're going to add asset 2 that has 30% standard deviation. So everybody get this? We're adding an asset that has higher risk. Almost double the risk is asset 2 than asset 1. All right, let's go ahead and calculate the portfolio return. This is just a weighted average return. So we're going to take 80% times the almost 10 and 20% times the almost 16. We're going to get 11.14%. All right, that should be a pretty basic calculation. Portfolio variance, we're going to square the weights and we're going to multiply by the variance. And then we're going to take, in the last part, we're going to take 2 times the 80% times the 20% times the covariance. And we get 0.23. Take the square root of that and we get 15.39. And so what I want to do is let you guys pause the video. Make sure you can compute that 15.39. But before you do that, what should you be doing? You should be jumping up and down like the Eagles were doing the other day when the Bears missed the 40-yard field goal. We should be high-fiving each other. Look at this. What did we do? We started out with 17%. We added a 30% standard deviation to our portfolio. We increased risk, but what has happened to the total risk of our portfolio? It has gone down. Oh my gosh, this is the beauty of diversification. We added a riskier asset and we reduced risk. This is why the CFA Institute puts so much emphasis on diversification and requires us to be able to do the math. It's one thing to just be able to say, oh yeah, diversification reduces risk, but now you know the mathematics behind it. All right, so go ahead and pause the video. Make sure you can do that math. Now let's go ahead and talk a little bit more about correlation. So the LOS asks us to describe the effect when we invest in securities or assets that are less than perfectly correlated. All right, so what do we say? We know that the range of correlation is from -1 to +1. If the correlation coefficient between two assets is +1, we say they are perfectly positively correlated. Are you ready for this? That means that when one goes up by 10%, the other one goes up by 10%. One goes down by 8%, the other one goes down by 8%. Now, this doesn't have to be a one-to-one, a day-to-day change, but over time, if you invest in one asset, it's exactly like investing in the other asset. And then the flip side of that is if the returns are perfectly negatively correlated, you have one going up by 10%, then the other one goes down by 10%. And then this one goes down by 8%, then this one goes up by 8%, and that happens over time. And of course, if the correlation somehow turns out to be exactly 0, what that means is this goes up by 10%. You have no idea what this one is going to do. That means they are not related. So this one goes up by 10%. This one could go up by 10. It could go up by 5 or down by 4 or down by 100 or up by 1,000. It could be anything. That's what a correlation coefficient of 0 means. Now let's take the extreme examples. So if in fact we are investing in assets that are perfectly positively correlated, then there are no benefits to diversification. There is no risk reduction. Buying 50% of one and 50% of two, if these two are perfectly correlated, is exactly like buying 2 shares of one and 2 shares of two. There is no diversification benefit. Okay? And then if the assets are perfectly negatively correlated, then there is a total risk reduction. But if they fall somewhere in the middle, that's where most of the stuff on the exam is going to fall, then there is a diversification benefit. Let's go ahead and work through a couple slides that will illustrate this point. All right, when the correlation is 1, notice what we have here. Let's just suppose we invest half our wealth in asset 1, half our wealth in asset 2. And expected returns and standard deviations are both 20% and 30%. So our weighted average return, that's 20%, nothing fancy there. And our portfolio risk is going to be 30%. And there you go. The math shows you that you get the 20 and you get the 30. But here's the thing. Suppose that asset 2 had a 30% return and a 50% return. And forget about what that means in terms of individual risks. But just let's focus on the mathematics. Well, the portfolio risk just becomes a weighted average. What did I say? 30 and 50? So the standard deviation for those two would be 40%. But the important point here is when there's a correlation of 1, you get no benefit from diversification. All right, how about when correlation is 0? And here's the cool thing. Notice that when we compute the portfolio return, that doesn't have anything to do with risk. So the return, expected return, is still the 20%, right? We had 20% back here, we've got 20% here, but what happens to portfolio risk? Now, before you look at that answer there over on the far right, which I'm sure you've already done, I want you to just think about this from a conceptual term. What we're going to do, I'm going to go back here to the formula. Look at that top formula. If the correlation is 0, then the covariance is 0. That far right term, the 2 times the weights, that drops to 0. So if you're adding 0, what has to happen? Well, risk has to go down. So notice on the far right column there the far right part under the square root sign, we have a 0. So that entire right-hand term drops out, so risk falls to 21%. Now, before I hit the down button and go to the next case where correlation is a -1, what do you think's going to happen? What do you think's going to happen if there's going to be a negative, perfectly negative correlation between asset 1 and asset 2? I'll give you 5 seconds to think, all right, what's that number going to be? So look at the 21. I'm going to go down. And what do you think it's going to be? Of course it's going to be 0. But note the portfolio return is still at 20% because now what we're doing in that far right column, now we're multiplying by a -1. So that third term is a subtraction. And if you look at the math, it's going to exactly offset. All right, so think about this. You can take asset 1, which is risky. You can take asset 2, which is risky, and you can put them in together a portfolio. If their correlation coefficient is a -1, you're going to get 0 risk. Now, this of course, is the scenario in kind of a fantasy world, maybe in a vacuum, because as you probably know, there are not too many, if any, financial securities out there that are perfectly negatively correlated. We'll talk a little bit about that when we get to the derivatives reading. All right, how about risk aversion? This is really an interesting concept. You know, just the general commonsensical interpretation of risk averse means that, you know, someone is risk averse, that means they don't like risk, right? They're averse to taking risk. And that's probably pretty true as it applies to modern portfolio theory, but we need to be a little bit more sophisticated in terms of levels of risk aversion. So let's go ahead and take a look at an example. I'm going to give you 2 options. Which one would you choose? Let's suppose that I said to you, there's going to be a gamble, whatever that gamble it is. Maybe it's a roll of the dice, maybe it's a football game, maybe it's a flip of the coin. Forget about what the gamble is. But let's suppose that I say to you, hey, no matter what happens with the dice or the football game, I'm going to pay you $100. Or your payoff depends on the outcome of the gamble. If you win, I pay you $200. Or if you win, I pay you $200. If I win, then I pay you $0. Oh my gosh, then what? Well, if you do the math, let's just suppose it's a flip of the coin, 50% of 200 and 50% of 0. That gets you an expected outcome of 100. So which one are you going to pick? Are you going to pick option 1 with the guaranteed $100, no matter how the outcome materializes, or option 2, which going into the gamble, you're going to have an expected value of 100. So either way, before the gamble, you're thinking you're going to get 100. That's what expected value means. Well, your choice of option 1 or your choice of option 2 is going to tell us a lot about your attitude towards risk. What do you think? Someone who is going to take the guaranteed $100, this person is avoiding risk. But the person who's going to gamble and say, hey, I have a 50% chance of getting $200, this person likes risk. And so do you see that the finance term of risk aversion has to be a little bit more sophisticated than just a general idea of, oh, we don't like risk. All right, we have risk seekers, risk averters, and then risk neutral individuals. And so a risk seeker is somebody who seeks out risk. So they're going to look for those risky opportunities, but they're also going to say, okay, I need some return for taking that risk. Risk neutral individuals, what they want to do is they want to pick the highest possible return regardless of risk. And I have a picture of these here in just a few minutes. Risk averse, these are very low appetites for risk. They would rather accept a lower certain return, that's what we're talking about with that option above, than a substantial risky investment. And then risk tolerance is the term to kind of describe the total amount of risk that an investor is willing to take. And when we get to the policy statement, it's going to be really important for us to distinguish between a client's ability to take risk and a client's willingness to take risk. We're going to combine those two and call that risk tolerance. How about this concept of an efficient frontier? Man, this is such cool stuff. This goes back to 1952, and Harry Markowitz, as a 25-year-old doctoral student who came up with all this stuff, he really he married statistical concepts with economics concepts. Remember, in 1952, there was no discipline known as finance. It was all economics. So he came up with this concept of an efficient frontier. An efficient frontier is a locus of points which provides the greatest return at each given level of risk. I'm going to show you a picture of this in just a second. Now, clearly, what this means is if there are efficient portfolios, there must be inefficient portfolios. So we need to understand this concept of domination. And so the efficient frontier is going to be the locus of points that dominates those inferior, or can we call them inefficient portfolios. Now let's take a look at an example. On the next slide, I have a picture. Let's suppose that we've got 20 stocks, 20 different assets. And with those 20, with the help of a computer, we calculate all possible portfolio combinations. So think about the easiest portfolio combination would just be an equal weighting in all 20. But with a computer, boy, you can just have really thousands or maybe even hundreds of thousands of different weights. All right, so we can plot all of these different possible portfolio combinations. We're going to find what's known as the minimum variance frontier. We're going to find this global minimum variance portfolio, and then we're going to find the efficient frontier, which is subject to the dominance rule. All right, so keep that stuff in mind, and let's go ahead and look at a picture here. All right, so notice on the vertical axis, we have expected return. That's the total portfolio. And then on the horizontal axis, we've got portfolio standard deviation. So we've got return going up and we've got risk going sideways. So that line, boy, I'm just terrible with colors. What color would you call that? Light brown. That light brown is the minimum variance frontier. But we're going to eliminate part of it because we really don't care about the part at the bottom below that big star on the left. All right. So notice the stars on that light brown curve are bolded in red. Those are called efficient portfolios. The blue stars inside of that, these are inefficient portfolios because you would never want these portfolios. You can move either upwards or to the left and get something that you prefer. All right, so this is the way I want you to think about this. If you could pick any place on this graph to locate your portfolio, where would it be? There's no doubt that you would go to the origin and you would then go right up the vertical axis all the way up to the top. You would want to have lots and lots of return with no risk. But unfortunately, it's not possible. It's not possible to get lots and lots of return without taking any risk. So those portfolios up in that northwest corner, that's where we want to be. We want to be in the northwest corner. Those are called unattainable portfolios. And I want you to do some kind of a link between that efficient frontier and the newscaster on the Weather Channel. What do? They show you your state or your country or wherever you are, and here comes a front. And this front is moving along. Here in Pennsylvania where I live, I always think of that westerly moving front. It goes up towards Erie. This is what we want to do. We want to be way up there. And as good financial analysts, that's what we're trying to do. We're trying to push that efficient frontier for our clients up to that northwest corner to get more return and less risk. But sooner or later, it's not possible. We just hit a barrier. It's just not physically or mathematically or financially possible to get to that northwest corner. All right, so let's talk about an important point on there. Notice the big star, the global minimum variance portfolio. That's at the point where the curve begins to swing backwards. So from that global minimum variance portfolio all the way down to the right bottom corner of the graph, you can kind of take a little pen and cross off all that stuff. Even though it's part of the total minimum variance frontier, it's still inefficient. We don't want any of those portfolios down there. What we want is from the big star, then curved all the way up to the top right. That's the efficient frontier because it dominates all other portfolios. Now, let me go ahead and just give you a couple of highlights here that I talked about in the previous slide. Portfolios lying on the efficient frontier offer the maximum expected return for their level of risk, of course. Efficient portfolios use risk efficiently. What this means is that we make this entire decision in a mean variance framework. Now, let me just do a comma here. Let me go back to an earlier slide. We're making the assumption, not just we, but Harry Markowitz and William Sharp, all these dudes, they made the assumption that asset returns can be fully described by their first two moments, the mean and standard deviation, which means there's no skewness and there is no kurtosis in this discussion. What we're doing is we're trying to get the optimal mean variance choice. Another way to look at risk aversion is through this concept of utility. I remember in my very first economics class back in 1981 or whenever that was, I had never heard of this concept of utility before, and the professor kept saying utility, utility. I don't know what it meant for I don't know how long, if it was 10 minutes or 10 weeks, but it finally dawned on me that it meant satisfaction. And so clearly then it clicked for me. Yeah, I get some satisfaction out of eating an apple or going to the movies. But in this modern portfolio theory framework, our satisfaction can be described by mean and variance, mean and standard deviation. So our satisfaction comes from doing what? Trying to maximize return at each given level of risk. And we're going to rank these returns inside of this utility. Now, the assumptions are that investors are risk averse, that you can rank them according to means and variances, and that they are internally consistent, which, let me just swing back here. Internally consistent means that, look, if one of those blue stars is inefficient and another one is inefficient, well, then they both have to be inefficient, internally consistent. All right, let's take a deep breath and go back to economics, this concept of an indifference curve. This is really important. An indifference curve is a combination of risk and return pairs, okay, that an investor would accept given a level of utility. So let me give you a quick example. You might have an investor who is indifferent between owning a share of stock that has a 10% return with a 15% standard deviation and owning a stock with a 12% return and a 17% standard deviation. You would be indifferent. There would be the same level of satisfaction, the same utility. So they would be indifferent between owning those two financial securities. Right now, an indifference curve, this is important. All points along an indifference curve have the same utility. And each individual investor might have their same level, is going to have different levels of utility, but each investor on that utility curve is going to be indifferent between and among all of those choices. You know, that concept of indifference is really an economics term, but we're applying it here in the risk-return framework. All right, and this is what indifference curves look like. Here we go. We got expected return on the vertical axis, standard deviation on the horizontal axis. And all we're saying here is that the blue line has much higher satisfaction than the dotted blue line, and then the really heavily dotted blue line. So we have low and moderate, high utility. And all this does is summarize the concept that I said earlier. What are we trying to do? We're trying to move to that northwest corner. So the closer we get to that northwest corner, the higher is our satisfaction. The higher is our utility. Way down in the bottom right, we have low utility. We don't want to take lots of standard deviation. We don't want to take lots of risk and have a low return. Now, here's a quick picture of the difference between those three types of investors that we had a few slides ago. Look at the risk lover. There's the blue dotted line that goes down. What does the risk lover mean? The risk lover says, you know what, just give me more standard deviation. I don't care even if my return goes down. A risk neutral investor, notice that's a horizontal line. That's parallel to the horizontal axis. What that risk neutral investor says is that, look, I want my expected return, whatever that is, let's say 10%. I don't care how much risk I have to take. I can take 5% risk or 10% or 20% risk. I don't care as long as I get my expected return. And then there are different levels of risk aversion. So someone who has very high risk aversion is going to have a steeply sloped indifference curve there. That's high risk aversion. And then someone with low risk aversion, that's the dotted line right above the risk neutral, they're going to have a much more flatly sloped. Okay, so remember, highly risk averse investors, they have steep slope. Lowly risk averse investors have flat slopes. All right, what does this mean if we, here, let me do this. Let me go back here. What does this thing mean? Now, this efficient frontier is the frontier of risky stocks. But what if we add a risk-free asset over to the vertical axis? Well, that's what we're doing in this slide here. And this is called the capital allocation line. So notice there's an intersecting point on the vertical axis. There's the R sub F. That's the risk-free rate of interest. And here's the cool thing about this, that when you add a risk-free rate of interest to a risky portfolio, and notice that that's a blue star, and that doesn't mean that it's not efficient. Could have been a red star. It's probably just any star there. But when we combine a risk-free asset and a risky asset, the relationship between risk and return becomes linear. This is an amazing result. Let me just swing back here. Look. This efficient frontier, that is a curve. There's no way that that's a line. Now, it looks like it might be a line when you get up to the far right, but it's still not. Down here, wow, the relationship becomes linear. All right, so explain the selection of an optimal portfolio. So when you talk about the capital allocation line, start with the risk-free rate of interest and remember that the relationship is now linear. And that's why you can come over to the right-hand side there and you can look at the capital allocation line. It's a line, right? It's linear. And there's the formula. That's a good one to remember. Now let's go ahead and combine what we've done over those last couple of slides. There's the dark brown capital allocation line. And there are some indifference curves. So note, where would we want to be? Clearly, our preference would be on Indifference Curve 1 and find portfolio A and B. But those things are unattainable. So what do? We find the indifference curve that is tangent to the capital allocation line. That's the middle one. That's 2. That's the highest utility that we can attain. Now, indifference curve number 3, we don't like any point on there. I mean, we're going to be indifferent between point D and point C and point E, but because point C is located on that second indifference curve, on that higher indifference curve, we're going to pick C as our optimal portfolio. So we don't like D and we don't like E. We like C because it has a higher utility. We're going to get a higher satisfaction. I told you that was fun. That completes part 1. Part 2 is even going to be better. Maybe I'll do a cartwheel during part 2.